Greetings everyone. My name is Sharif Amit Kamran. I am a second year computer science PhD student at University of Nevada, Reno. Today I'm going to present our paper called Improving Robustness Using Joint Attention Network for Detecting Retinal Degeneration from Optical Coherence Tomography Images. Retinal degeneration is a type of retinopathy where the retinal subspace is damaged over time due to natural or underlying causes. It is estimated by the year 2070 the number of patients affected by diabetes could reach 1 billion, and every one-third of them might develop a condition called diabetic retinopathy. There's also age-related macular edema, or AMD, where with age, retinal degeneration occurs and results in vision loss or blindness. There are two other underlying causes which are of importance. One is cortical neovascularization, where blood vessels appear in the retinal subspace and is an advanced stage of AMD. The other one is drusen, where protein buildup takes place underneath the retinal layers. To diagnose the aforementioned conditions and diseases, we use optical coherence tomography, or OCT. Optical coherence tomography is a technique which uses low coherence light to understand morphological information of the retinal subspace. But the differential diagnosis is still dependent on expert ophthalmologist. The solution is to automate the process so there exists no room for human error. Different techniques have been proposed so far, ranging from image processing using edge detection and graph path segmentation. Machine learning approaches have also been proposed, whereas SVM and random forests are utilized to diagnose these conditions. And most recently, deep learning models have achieved state-of-the-art results in different classification and segmentation tasks. It should be mentioned that deep learning models require huge amounts of data and hyperparameter tuning to get a reasonable score. The problem with the deep learning architecture is that it does not generalize well on unseen test data outside its sample distribution. Moreover, classification architectures consist of dense layers in the topmost part, which squashes the previous spatial features into linear features. Due to that, spatial information is lost while training the architecture. Most importantly, the image acquisition system and techniques can be different for OCT imaging, so the quality and features of the data might vary, resulting in bad performance. To better understand our proposed architecture and method, we need to go over the basic backbone of a residual classification architecture. The architecture consists of multiple residual layers in subsequent stages. In each stage, there is a downsampling layer, and after the final stage, there is a global average pooling layer. The final layer is a dense layer followed by softmax activation. Some architecture with the aforementioned features are ResNet 50, OpticNet 71, and MobileNet version 2. Our proposed architecture consists of a supervised encoder, a supervised classifier, and an unsupervised decoder. The supervised encoder and classifier are similar to any classification architecture, whereas the unsupervised decoder is a generic module that can be attached with the supervised encoder. The supervised encoder has residual convolution layers followed by 2x2 downsampling layers in each stage. The unsupervised decoder consists of multiple 2x2 upsampling layers which interpolates output to a higher spatial dimension and retains the spatial features. There are skip connections from each stage of the supervised encoder that are connected to the unsupervised decoder. These connections contain an attention module that element-wise adds features with each output of the upsampling layer. Both the unsupervised decoder and supervised classifier have their separate loss function. They are adaptively updated using a dual loss scheme while training the network. To demystify the mathematical operation in the skip connection, we formulate an equation for the attention module. Here S signifies output from each stage of the supervised decoder, U denotes the output of each of the paired upsampling layers having the same spatial dimension, and lastly C denotes the convolution operation which is applied on the output of S to make the depth of the feature map same as U. For dual adaptive loss, we use categorical cross entropy for the supervised classifier, whereas we use mean squared error for the unsupervised decoder. Both the losses are first multiplied by their paired weights, and then they are added together to get the total loss. We initialize the loss with a weight of 0.5 for both the supervised and unsupervised losses, so both are equally weighted to generate good results. While training, the losses are adaptively updated to prioritize either the unsupervised decoder or supervised classifier. We can see the number of parameters have increased in 3 residual architectures. where the unsupervised decoder has only 0.5 to 2% of parameter increase. This is negligible given how large the supervised architecture is. It also proves that this model can be attached with little computational overhead for training. We use the following hyperparameters for training, where the batch size is 4, the number of epochs for training is 30, initial learning rate is 1 A inverse 4, whereas step decay is 1 A inverse 1. We use adaptive learning rate for training our joint architecture. If for 6 consecutive epochs, the validation loss doesn't decrease, we multiply the step decay with the previous learning rate to get our new learning rate. For training, we use the Srinivasan 2014 dataset, which consists of 3,231 images with 2,916 images for training and validation, and 315 for testing. The dataset consists of 3 classes, namely normal, AMD, and DME. We use 5-fold cross-validation for training our networks. For unseen data distribution, we use OCT 2017 dataset. The dataset has 1,000 images for testing and has 4 distinct classes, out of which 250 are for normal and 250 are for DME. We will use this to see if the architecture can distinguish the same classes of images from different data distribution acquired from different methods or systems. We use the following 3 metrics, namely accuracy, sensitivity, and specificity, for evaluating our models and previous architectures. For Srinivasan 2014 dataset, 2 of our joint networks achieve better results for 3 metrics compared to the vanilla architectures. However, for OptiNext71, the network gets worse results. But this can be seen as a good indicator that our network is not being overfitted with the training data distribution. As we can see from the next table, which is for unseen data distribution, our model achieves better performance on OCT 2017 dataset, whereas the vanilla architectures get worsened performance. The most weak results is from OptiNext71, which is 25.6% less accurate than the seen data distribution. This also proves our hypothesis that retaining spatial information while training an adaptive supervised unsupervised joint attention network can improve accuracy of any classification architecture for unseen data distribution. In future, we hope to extend this work by collecting and annotating dataset for OCT segmentation. We aim to create a new pipeline for training and deploying segmentation networks for OCT images. Lastly, we would like to improve the robustness of our segmentation architectures for better disease diagnosis. With this, I conclude my presentation. Thank you.